NigerCon 2024, the IEEE International Conference on Electrical Computing for Sustainable Development. The title of my paper is Comprehensive Analysis of Black Hole Attack on Ripple in Static, Mobile, and Hybrid Network Environment. My name is Faisal Ali Garba, and I have MSc, and I'm currently enrolled for a PhD program in Ahmad Bello University, Zaria. This is the outline of my presentation. Abstract, introduction, literature review, methodology, result and discussion, conclusion, and future work. Abstract. The routing protocol for low-power and lossy networks, RPL, extensively applied in IoT application is susceptible to the black hole attack, wherein hostile nodes discard packet without transmitting, resulting in considerable loss of network performance. This attack jeopardizes the reliability and usefulness of ripple-based networks, particularly in crucial applications like environmental monitoring and healthcare. Understanding the effect of black hole attacks in diverse network environments, static, mobile, and hybrid, is vital for creating personalized security solutions. Every scenario provides various issues, including the stability of static networks and the dynamic nature of mobile and hybrid setups, which determine the severity of the attack. This study performs a comparative investigation of the impact of black hole attacks on ripple-based networks in static, mobile, and hybrid scenarios. Simulations were done with varied node densities, 10, 20, and 30 nodes, and different percentages of malicious node, 10%, 20%, 30%. Key performance indicators such as packet delivery ratio, average end-to-end delay, overhead packet, energy utilization, and throughput were investigated across these conditions. The analysis suggests that static networks, however, more robust random attacks, are susceptible to disruption when black hole nodes interfere with important links. Mobile networks incur the highest performance deterioration due to frequent route changes and increasing energy demand. Hybrid networks, having both static and mobile nodes, demonstrate immediate susceptibility but are more affected by mobile attackers. Overall, the statistics imply that mobility improves the impact of black hole attacks. The findings underscore the need for environment-specific security solutions in ripple-based networks. Static networks demand stronger detection systems for targeted attacks, while mobile and hybrid network environment need adaptable, low-overhead security solutions that can handle changing topologies. This insight will inspire future attempts to increase the security and dependability of IoT networks under black hole attacks. Introduction. The routing protocol for low-power and lossy networks, RPL, was established by the Internet Engineering Task Force, IETF, particularly to solve the special difficulties posed by the low-power and lossy networks, which are often found in Internet of Things applications. So these LLNs are characterized by devices that have limited power, memory, and computational capabilities, and by communication links that are often unstable and have poor bandwidth. RPL is particularly well suited for this circumstance due to its ability to operate inefficiently in networks with high packet loss rates, low data transmission speed, and strict power limit on the devices. RPL employs destination-oriented directed acyclic graph (DODAG) to manage data routing throughout the network. The protocol supports three types of traffic patterns common in IT applications: multi-point-to-point for collecting data from multiple sensor nodes to a central sink, point-to-multipoint for disseminating control information from a central controller to multiple nodes, and point-to-point for direct communication between the nodes within the network. So, problem statement. The black hole attack is a major threat to the stability of routing protocol for low-power and lossy networks, which is extensively employed in IoT scenarios. In this attack, a rogue node purposely dumps all data packet it received instead of forwarding them to the intended destination. Unlike other attacks that might comprise displaying positive routing metrics to encourage traffic, the black hole attack does not require any such dishonesty. Instead, it relies on normal routing processes to be picked as a parent node by surrounding nodes, after which it proceeds to drop all incoming packets. The major result of black hole attack is substantial decline in the packet delivery ratio, which measures the proportion of accurately delivered packet versus the total number of packets transmitted. So as the malicious node dismisses the packet, the network experiences considerable data loss, which can be harmful to the overall performance in vital IoT applications where consistent data delivery is crucial. The routing protocol for low-power IoT network was established by the Internet Engineering Task Force. All right, so I already read this. Black rifle and black hole attack. The routing protocol for low-power IoT network is a distant vector routing protocol developed to suit the needs of networks defined by constrained resources such as low-power IoT network, frequently seen in the IoT deployment. Rifle has become the standard protocol for routing such systems in the constrained IoT devices, offering a robust method to manage inherent limits of the low-power IoT networks, including limited power, memory, and processing capabilities, as well as the reliability of communication channels. Rifle organizes the network topology into a hierarchical structure known as the destination-oriented directly acyclic graph. And the DODAC executed at the node, sometimes referred as the root or sink, which act as the last destination for data inside the network. The black hole attack is a serious and stealthy routing attack targeting the routing protocol for low-power IoT networks. So, review of related works. Reference 2 offered a detailed assessment of black hole attack impact on low-power IoT network. Their research focuses on black hole attack effects on network performance across diverse contexts, such as packet delivery ratio, energy consumption. However, their study centered exclusively on static and mobile environment and did not analyze the hybrid network scenarios, which combine both static and mobile nodes. And the reference post studied the impact of mobility or rifle performance in IoT networks. Their research focuses on understanding how mobility affect the reliability of communication, specifically under black hole and selective forwarding attacks. While the supply is split insight into the mobile environment, the study lacked an emphasis on static or hybrid network topologies. Reference 5 did a comparative examination of the many security vulnerabilities in rifle, including black hole, sinkhole, and version number attacks, utilizing the Contiki OS and the Kuja simulator. While the study focus presents a good evaluation of attack performance using metrics like average power consumption and packet loss, it does not really address the behavior of these attacks in hybrid network environment, which are becoming increasingly prominent in IoT applications. So, gaps in the literature, how this paper addresses them. We have limited analysis in hybrid network environment. Most studies, such as those by 2 and 5, focus primarily on static and mobile network environment when evaluating the impact of black hole attacks. Hybrid systems, which combines both static and mobile nodes, have not been sufficiently explored in terms of how black hole attacks manifest and affect the network performance. Given that hybrid networks are becoming increasingly frequent in large-scale IoT development, this constitutes a considerable gap in the literature. Focus on individual attack metrics. Previous research, especially the work of reference 4, examined the impact of black hole attack on several performance parameters such as network overhead and packet delivery ratio, typically in isolation. However, there is a scarcity of detailed study that assess multiple performance characteristics simultaneously, like VDR, latency, energy consumption, and throughput, in a consistent framework across the varied network topologies. Inadequate. So these are all the research gaps that this research aims to addresses. So for the simulation environment, we make use of the Contiki operating system, Contiki 3.0, and the simulator we use the Kuja simulator, and all the simulation parameters are being presented in this particular table 1, as we can see them. All right. So so we move over to the simulation results. So in the simulation results, for 10 node simulation result, we have reference simulation and 10% malicious node, where 10% of the node are malicious, and a case where we have 20% of the node are malicious, and a case where we have 30% of the node are malicious. And we can see the various results that we obtain for the PDR, for the average end-to-end delay, for the overhead packet, for the energy consumption, for the throughput, as you can see in table 2, 10 node simulation results. And then we have the graph of the 10 nodes simulation in a static network. This is the simulation result for 10 nodes in static network. And then next we have for 20 node simulation result of static nodes, 20 static nodes where 20 nodes are being simulated. And then we have the graph here as well. Then we have 30 node simulation results, static nodes. And then we also have their graph here. And then we have 10 node simulation result for mobile nodes, and their graph is also here. And then we have 20 node simulation result for mobile nodes, and the graph is also here. Then 30 node simulation result for mobile nodes, and the graph is also here. And then we have 30 node simulation result for hybrid node static attackers, where we have the attackers are static, 50% mobile, 50% static nodes, 50% mobile nodes, 50% static nodes, and then the attackers are static attackers in this case. And then we have their result also in this particular table, and then we have their graph here presented as well. Then we have some node simulation result where we have hybrid node and also static attackers, and the total number of nodes is 20 in this case. Then we have also for 20 node in hybrid network static attackers. The graph is also presented here. Then we have 30 node simulation result hybrid node static attackers, and then we have graph showing simulation result for 30 nodes in hybrid network static attackers. Then we have 10 node simulation result hybrid node mobile attackers. Also their graph is here, and then we have node simulation result hybrid node mobile attackers, and their graph is also presented here. And then we have node 30 node simulation result hybrid node mobile attackers. Their graph is also presented here. So we have comparative analysis of the impact of black hole attack across different network environments. For the PDR, we have static networks generally maintain higher PDR as their stable topology reduces the chances of routing through malicious node. Mobile and hybrid networks, especially with the mobile attackers, experience significant packet loss, with mobile node networks showing the worst performance in terms of PDR. And so also for all the other parameters, average end-to-end delay, overhead packet, energy consumption throughput is also presented in this particular slide. Then we have conclusion. The study has offered in-depth investigation of the black hole impact on ripple-based networks across static, mobile, and hybrid networks. Through extensive simulation, essential performance factors such as PDR, average end-to-end delay, overhead packet, energy consumption throughput were examined under varying percentage of malicious nodes. And for the future work, we hope to work on the sinkhole attack. So these are the references. Thank you.